Today, I want to talk about how the 6502 handles interrupt requests and how I am using that in my overall system. So let's turn to the data sheet for the 6502 processor. The interrupt request signal, which is on pin 4, will handle interrupts when that pin goes low if the interrupt disable flag is not set on the status register. So first of all, if you want to handle interrupts, you need to turn on interrupts by clearing the interrupt flag on the 6502 status register. And then you have to provide a low signal on pin 4, which is interrupt request signal. Now, here it tells you that the interrupt request low level should be held until the interrupt handler clears the interrupt request source. In other words, we need to have a setup whereby we can trigger the interrupt signal to go low and then hold it there. And then we need a way for the computer to then turn that off and send it back to a high signal so that when the interrupt is handled. And one of the things that helps with this is that the 6502, when it enters the interrupt handler, it will automatically set the interrupt disable bit so that while you're handling the interrupt, additional interrupts can't happen. And that's one of the reasons why it works the way it does. What you need is for the computer to be able to disable other interrupts while it's handling an interrupt, and then be able to say, I've handled that interrupt. And then it can go back to normal code. And if there's another interrupt, then it can handle that interrupt and so forth. So that means we need the following three things. We need a way to set and hold an interrupt request. And two, we need a way for the computer to know what triggered that request, because if you have more than one type of interrupt, you're going to need to be able to distinguish between them. And then we need a way for the computer to acknowledge, which is to say reset the request. So let me talk about how we'd want to do that. So how we're going to do that is to use our old friends, the SR flip-flop. The idea of an SR flip-flop is that you can use one signal to turn the flip-flop into an on state and then a separate signal to turn it to an off state. That's exactly what we're going to want to do here, because we're going to want to have a way for the interrupt, whatever's causing the interrupt, to turn on the interrupt. And then we're going to want a way for the computer with a separate signal to turn off the interrupt. So an SR flip-flop is perfect for that. And there's two types. There's types that you can build with a NOR gate, and there's types you can build with a NAND gate. If you use a pair of NOR gates, then a positive signal on the say on the S line, the set line, that's the S stands for set and the R for reset. So a positive signal on the set line, that will cause an OR gate to go high, which means the NOR gate will be caused to go low because one or more of the input signals is high. So the output will be low. And that'll cause they'll call the input on this gate to be low. And if R is currently being held low, which is the normal state, so hold it low for this type of flip-flop, then both of these are low. So this output is low. So this output is high. So this goes high. So now you've got high, high. And so you have this output low and this output high. And that's why this output is called Q. If you then set S low, so S and R are both low, well, you still have this output, this input here being high, which means this output is low. This is low and this is low, so so the output here is high, and so it maintains that state. And then, likewise, if you then were to turn the R high, flip the R from low to high, then it'll reverse it, because now this is high, so the output of the NOR gate is low. So this is low and this is low. So the output here is high and so forth. So S to set, R to reset. You have a Q and you have a Q prime output, which is the opposite of the Q output always. And then you have the NAND gate, and I could go through the whole thing, but it works exactly the same, except instead of a positive signal, you use a negative signal. So if your signal is normally high and the interrupt is caused by a negative, then you would use this sort of gate. And I'll be using both gates in this setup, and I'll show you how. So, but this otherwise it works the same. You will notice that with the NOR gate, the output when you the Q output is opposite on the opposite output, opposite gates output from where the set is, and on the NAND gate it's the same. And that's related to the fact of something I talked about in my last video about how you can think of an AND gate as an OR gate for negative logic. And this is using that property. So these are like OR gates for negative logic. And if you consider the output negative instead of positive, then you can see that these would be completely symmetric. In other words, this could, if you considered Q to be true when it's negative, then this would be the Q prime output and this would be the Q output. But we're not using it that way. We're just going to use it in the normal way where we want a Q high signal. Now, I have additional complication with my system. Because I have this single-step debugger board, I also need it so that when the computer is in debugger mode, it's not going to handle interrupts, because the interrupts would get in the way of handling, of being able to single step in the computer. And we also need it so that when we're in a wait condition, if you recall, that when you call the 65CO2 wait instruction, then the halt line will go low, or the ready light line will go low, and the computer will wait until there is a negative on the interrupt. And that doesn't matter how long that interrupt. That could be a very short pulse of a negative on that on the pin 4, the IRQ pin, and then it will begin processing again. And because of that, if we were to just be in the wait, so if I press this and now the computer is in the wait condition, I have this set so that when reset is low, the light is on. So the reset is low now. So the LED is on. It's waiting for a negative on the interrupt. And if my interrupt system was providing interrupts to it right then, during this time, it wouldn't be able to wait. But now it waits until I push the button because I can disable the interrupts while it's waiting. So let me show you how I've got the logic for that set up. So I've got two kinds of interrupts that I want to do. And one is a vertical blank interrupt. So I want to be able to tell when I'm entering the vertical blank because I want to do some work on what's on the screen during the vertical blank interval. And I want to be able to do other stuff when I'm not in the vertical blank interval. So I'm creating a signal, and I'll show you that in a minute. I'm creating a signal called VBS, vertical blank start. And that's just a quick pulse that I set up with my video card so that the output of the video blank signal will just pulse for a very short time. I have it for 3 clock pulses. So that's for 3 of the 10 megahertz pulse signals. So for 0.3 millionths of a second, this signal will be pulsed high. And that will cause this to go high. And when this goes high, then it goes to this NOR gate. This is high, so the output of the NOR gate will go low. It goes through this NAND gate, which I'm using as an inverter by tying the two inputs together. So this is low, so this will go high. And since this is high, then this will go low only if this output is also high. When is this output high? Well, here's how I do the disabling. I have the debug signal, and that is when I'm in debugger mode, then I have that wired up so that that goes into one input of this NOR gate. And I also have at my register at address 5070, bit 4 I have tied to this. So when bit 4 when debug is low and bit 4 is low, then this output, both of these are low, so this output will be high. But if either of these go low, high, then this output will be low. Then the interrupts are enabled because then when this signal is high, then this signal will go low. So when either of these signals is low, then the output of the NAND gate will be high, and the output of this inverter, which I also built out of a NAND gate, will be low, and that generates the interrupt request. So I was able to do that with just adding a couple of gates to a couple of chips to my system, because I'm using the actual gates to do inverters. So I have an inverter here, which is a NAND gate. I have another inverter here, which is a NAND gate. So you can see here, I need 3 additional chips. So I'm using this as a quad, this quad 2-input NAND gate chip. This is another quad 2-input NAND gate, and then these here are from the NOR gates. Now, the signal that I'm using to generate that video blank start, I had to create a new signal. Fortunately, because I'm using this video card that drives all its logic from a ROM chip, I could just reprogram that ROM chip. So my signals used to look like this. I had the horizontal sync signal, the vertical sync signal. I had, and the B just means that they're active low. I had a horizontal blank interval signal and a vertical blank interval signal. And I had a horizontal counter reset. This is the signal. Again, it's a negative going signal. This is the signal that resets the counter to 0, the horizontal counter. I had the vertical counter reset bar, and that sets the vertical counter. That resets the vertical counter. And then I had I have a signal to indicate when we're at the blank interval, and I had a signal to indicate when we're in the display interval. Now I am using both blank interval and display interval, except to get the display interval, I'm actually just inverting the blank interval signal. So I don't need this signal actually, because I need a display interval signal, but because it shortens the wires, I'm using it by inverting the blank interval signal up in my logic chips. So I'm not using the horizontal blank interval signal anywhere. I'm not using the vertical blank interval signal anywhere, and I'm not using the display interval signal. That's not true. I am using the vertical blank interval signal just so that the computer can check a register to see when it's in the vertical blank. So what I did was I rewrote the output so that the signals look like this now. So now the signals look like this. I have the vertical blank interval. I moved that to pin 7 for no particular reason. It just was simple, made things a little simple to wire. So I moved the vertical blank interval to bit 7, and I got rid of the horizontal blank interval signal, which I did not need. So this one was just reserved, unused. If I need another signal from the video card, I have a place I can put it. And here I have the video blank start. Video blank interval starting signal, the VBS signal. And let's see. If I go back here, you can see that how I did that is I just say if Y is equal to VB start. So in other words, VBI start. In other words, I'm on the first row of the vertical blank interval. And if X is in the range 0, 4, so in Python, that means it'll take the values 0, 1, 2, and 3. So if I'm in that range 0, 1, 2, or 3, then I add the vertical blank signal by ORing it with the existing signals. So that's really the only real change I had to make here, other than I did change, I changed the bit that the VBI signal was on, and I got rid of the HBI signal. And so now I have that vertical blank start signal, and it's just 0 and 3. So I guess it's actually 0.4 microseconds in width. Shorter might work, but this seemed like a good place to go, and it seems to work for me. So that's this signal here. So this signal here runs up. This is the vertical blank start signal, and it runs into this NOR gate flip-flop, and I've created that by just running the output of gate 2 into the input of gate 1, and then I'm crossing the output of gate 1 to the inputs of gate 2. One thing to be aware of with the NOR gates is that they are wired the opposite of most other, their inputs and outputs are opposite of most other 74 series chips. So almost all the chips that are 2-input chips, quad 2-input chips, pins 1 and 2 are inputs, pin 3 is an output, 4 and 5 is an input, 6 is an output. And then it's wired the other way here. You can see pins 10 and 9 are inputs, 8 is an output, and 12 and 13 are inputs, and 11 is an output. But if you look at the NOR chip, it is wired the opposite of that, so that 2 and 3 are inputs and 1 is an output. The effect of that is that if you wire if you wire your latch exactly the way that you would wire it for a NAND gate, then the inputs and out the position, the actual like location of the Q and Q prime outputs are the same as they would for the NAND gate. So I don't know if that's why the NOR gate is wired the opposite of every other signal, but I think it might be because it is very common to use NOR gates and NAND gates as SR flip-flops. So that's the latch, and the output of that latch I run up here to this. This chip is an SN74HCT245 transceiver chip. And this is basically all you need along with the address decoder. This is all you need for a read register. So this is my read register. It's wired to this address decoder. This is just a 74HCT138 address decoder like I've been using. But I wired this exactly like this one, which is for my write register. But this one, I wired one of the negative active gates of this address decoder to the read write, so that this is active only when the read write pin goes low. What I did was I ran the read write signal to a spare gate on this original NAND gate from the Ben Eater computer, and I ran it to a spare gate and wired as a NOT gate, so that this wire here is the opposite of the read-write bar signal. This is more of a write-read bar signal. And that goes to this gate, so that this gate is only active when we're reading. This address decoder is only active when reading. This address decoder is only active when writing. And by doing that, I can write to this. This is a D latch. I can write to this D latch using address 5070, and I could read from this transceiver using address 5070, and they don't conflict with each other. So anyway, I've got this wired up so that it goes to pin data line 0, 1, 2, 0, 3, which is the same data line that I used to deactivate it. So data line on this D flip flop, which creates a register for writing to at address 5070. The output of pin 0, 1, 2 pin bit 2 is used to reset this SR latch. So this goes to the R of the SR latch on this NOR gate. And this is, I said this wrong. This is this also goes to it's not 0. Yeah, pin 0, 1 to pin bit 2 of this transceiver. So it's bit 2 when writing, you can write to reset, and bit 2 here is how you can read which that interrupt request has been enabled, or that interrupt is requesting an interrupt. You can see this is also wired here to this input. So that NOR gate is this NOR gate here, and the other input of that NOR gate is running from the output of the other latch. So here I'm running bit 3, so that was bit 2, and so this is bit 3 is running over to the R, the reset of this flip flop. And here I have FG call and BG call. Let me explain what those are. So one of the things I want to be able to do with this system is that it will automatically detect when there's a collision between a foreground object and a background object, but not always, only in the places where you want it to. So because we have an extra 2 bits in our Ben Eater video card, we're only using 6 bits for color, I use 1 bit to determine whether the foreground or background image should be displayed, and I use the other bit, and that's bit 7. I use another bit 6, from each of the foreground and background RAMs is wired to run into to this NAND gate, and the output of this NAND gate is this wired into the flip-flop, and to this flip-flop, which then goes to the other half of this NOR gate. So this arrangement is here to set up when there is a collision between the foreground and background. And believe me, this caused quite a bit of frustration because when I'm running my memory test, let me restart that. When I'm running my memory tests, I was writing to background and foreground. The value could be anywhere from 0 to 256, which meant bit 6 and half the cases is going to, or at least a quarter of the cases is going to be high in both of these, which would trigger this interrupt. So I was getting that interrupt being triggered like, as much as 2-3 million times a second, which of course the computer couldn't keep up with handling that. So I had to rewrite the software a little bit in how it handles generating the memory test. And what I do is, first of all, before I even begin the test, I write all zeros to everywhere in the memory. And then when I'm testing the foreground memory only, I'm simply masking out bit 0 so that it can't write bit 6, I'm sorry. So it cannot write a 1 to bit 6. It can only write a 0 to bit 6. Otherwise, the test values are working the same. And that way, I'm never actually triggering this. So technically, I haven't really tested this part yet, but I'll get to that when the time is ripe. In the meantime, I am using the video interrupt, the video blank start interrupt, a vertical blank start interrupt. So I already explained how that's latching there. And then I have this bit here, which is, if you recall, is the VGA signal. In other words, this just tells whether we're in the vertical blank interval or not. That is running up to bit 7 in this latch. So I can use that bit to determine if I'm in the vertical blank interval or not. And bit 6 is attached to the blank interval, so that I can use bit 6 here to just determine, am I in a blank interval at all? And you might want to know that when you're coding, because you can do different things if you're in, say, a horizontal blank interval than if you're not in the blank interval. So for example, if the VGA signal is low, but the BI, the blank interval signal, is high, then we know that we're in a horizontal blank interval. I'm not trying to do a lot in the horizontal blank interval because it's very short. By the time I were to, for example, set up my memory so that I'm talking to I'm changed the clock speed to 5 megahertz, and I'm talking to the background RAM or the foreground RAM, and then after that's all done, like I'm out of clock cycles. I can't actually do anything useful. So I'm going to do all my useful stuff on the video card during the vertical blank interval. All right. So the output then from this NOR gate here runs into this NAND gate, which is just wired to be an inverter. That's this one here. And then from here, I wire into this NAND gate, which is this NAND gate here. So I've got the output from my interrupt request blocking signals wired into there. That's this output here is wired into there, and the other one comes from here we go. From here, that goes into the other half of this one. So then for the reset coming into here, that's this wire here. Here, this wire is from the so when this goes low, that's when the LED comes on. So that is telling me that I'm in debugger mode. So that debugger mode signal is coming in to it's jumpered here because I didn't have a long enough wire. So it runs, but it's running to the input to the other input of this NOR gate here. And from this, and then the output of that, as I showed, is running into this NAND gate here. So via this wire right here. So via this wire. Sorry, this one right here. That wires that into this NAND gate. And then the output of that is run over into here where it is NANDed with the resume button, That's this button here. That's what allows you to do your single stepping or to continue when you're done. And doesn't like that. Let's start over. And then finally, this one here is wired as the output, as the NOT gate, and that output is then run to the interrupt request signal on there. And that is how I'm getting the what I'm using it for right now is just for getting the real-time clock. So let's look at how that works. So a couple of things I have to do a little differently now. One is I can't just call wait, which is this byte $CB. This provides the wait opcode that has it wait. I can't just do that now. I have to jump to this wait subroutine. And what I do in this wait subroutine is I load A with what was in the video register value, and then I OR that with this inhibit IRQ, and inhibit IRQ is just set up so that it'll leave everything the same, except this bit will always be enabled. So I OR that with the inhibit IRQ, and then I store that to the video register, and then I wait, and that's the bit that disables the interrupts, so that when I hit a wait signal, for example, when I first started, I have a jump JSR wait early in the program, and now it's waiting for me to push this button. After I push the button, then what happens is it loads the value from the video register value again. And that hasn't been changed because I just OR'd it in memory in the A register with inhibit IRQ, and then I store that to the video register, and then I return. So that is how you now establish a breakpoint in your code, is that you have to call JSR wait rather than just calling the wait opcode. And then finally, for handling the interrupt, here's what I'm doing. First, I have to check what the interrupt is. So was it a foreground background collision, or was it a vertical blank start? So if it's a foreground, so what I do is I load the interrupt request register. That's loading whatever is set, bits are set on here. And you can see most of these I'm not using, I've just got them set to 0. But I've got the bit for the vertical blank start. I've got a bit for the foreground background collision, then 2 that are unused. And then I've got a bit for the, if I'm in the blank interval, and a bit for if I'm in the vertical blank interval. So I'm loading that register, and then I AND that with this FB column constant. And here you can see that that's a 1 in the appropriate bit 3. So I AND it with that, so that so this will be a 0 if that bit is not set, and regardless of any other bits, and it'll be a 1 if that bit is set, regardless of any other bits. Then I branch. So if that's equal to 0, then I branch. Then it's not a foreground background collision, and I branch to check VBS. So I load A with the IRQ register again, and I AND it with VBS to check for that bit. And VBS is you can see bit 2. And then if that's equal, and that is, say if this is a 0, then that means that bit was not set, and so then we just jump to done. If that bit is set, then we jump to handle VBS. And with handle VBS, here's what I do. I have a variable in memory called jiffies, and I increment that value, and then I load A with that value, and I compare that to 120. We'll talk about that number in a minute. It's decimal 120. And if that is a 0, then if that is not a 0, then I'm just done. I'm just incrementing the number of jiffies. A jiffy is my term for a 60th of a second. Oh, actually 120th of a second here, it seems. So then, but if the jiffies does get to 0, Then I load a 0. I store that into Jiffies. Or sorry, if Jiffies did get to 120, then I load a 0, store that in Jiffies, and I increment the number of seconds. And then I load that value of seconds and I compare that with a 60. And if it's not a 60, then I'm done. If it is a 60, I reset it to 0 and I increment the number of minutes. I do the same comparison. If it's a 60, then I'm done. And load a 0, reset the minutes. And then I increment the number of hours. And then that's it. Then I'm done with this interrupt handler. And then having handled the interrupt, now I just load A with the video register value, the original video register value, which I store every time I save something to it. And I OR that with VBS. So I'm ORing that with bit 2 so that bit 2 is guaranteed to be on and the other bits won't be touched. So whatever was in the video register value is still there. And then I OR it with VBS and I store that to the video register. And then I load the video register value back again, and this will zero out the VBS signal or bit 2 to VBS because it wasn't set before. And then I store that to the video register. And so now the video register back to what it was. And what that did was that did a very quick pulse onto bit 2 of this register, so this wire here. And so that runs to here, and that's what resets it right there. I do the same thing if it were to hit a foreground background collision. I run the handle FB collision, FB call subroutine, which is just a return. It's just a return from subroutine, and then I pulse the FB column bit, which is bit 3, store that, load it back, store it again. And so in that way, I can reset both whatever happens after the FB foreground background collision, whatever happens after the check VBS. So now I can have 2 different interrupt handlers for handling 2 different kinds of interrupts. And in addition to that, I have it set up so that my single stepper debugger board, which has been very, very useful, I have that still in function. So that's what I wanted to show you for today. If you've made it this far, well, I really appreciate it. I'd love it if you like my stuff, if you would subscribe and click the like button. That really helps me out a lot. I really appreciate all my viewers, and I especially appreciate the feedback. Oh, and I promised to talk about that 120. I'll be honest with you, right here. I do not know why I am getting this twice. I have verified very carefully that my VBS signal is 1/60th of a second, not 120 times a second, 60 times a second. I've done that with an oscilloscope and with a data analyzer. And yet, for some reason, I have to count up to 120, or it counts twice as fast as real time. So somehow this handler is getting called twice per. Even I also thought maybe I'm holding that VBS signal too long so that it's actually getting cleared, but I'm only holding it for 4 cycles, and clearly all of this takes longer to do than 4 cycles. So 4 clock cycles. So that can't be it. So if anybody has an idea why I'm getting this handled twice, I would love it if you could comment on that in the comments. And I do have one other strange thing that I wanted to share with you. I almost forgot. When I set the video register, this is what I call. I have a variable called bank select that 0 means the system RAM, 1 means the background RAM, and 2 means the foreground RAM. And I have a thing called block select, which is which block of the background or foreground RAM, since if you remember, I can only address 8K at a time of either of those. So the bank selects system RAM, foreground memory, or background memory, and block select, if I'm using background memory or foreground memory, selects which 8K block within the 32K RAMs that I'm using. So the interesting thing is I can go directly from system RAM to to the background RAM, and everything works. But if I go directly from system RAM to foreground RAM, then it does not work. The system hangs up and it does not run. And the way I solved that is right here, is that when I'm going to set foreground RAM, I first set the background RAM and set the block, and I store that to the video register. I do a couple of no-ops. This is because this will potentially have changed the clock speed, and I found when changing the clock speed, a couple of no-ops helps with stability. And then I load the foreground RAM, and then I jump to set block here, where I just go through the same thing, only now with the foreground RAM. If I'm doing background RAM, I can just go there. I can also go directly from foreground RAM to background RAM. I can go from any of those to system RAM, but I can't go from system RAM to foreground RAM directly. I have to go via setting background RAM first, and I do not know why that is. So why is my interrupt request handler being called twice as often as I expect? And why do I have to do this for the foreground RAM versus background RAM? Those are a couple of questions if somebody could answer, I would be very appreciative. Thank you very much. This is normally where I would say I will talk to you again real soon, but I'm going to let you in on my future plans, and it may take longer than my normal week or two between videos. The way I have this set up right now, I cannot do what I want to do. What I want to do is to have it so that background RAM scrolls with when I change these hardware registers that change these adders, so that I can scroll the background RAM vertically and horizontally. And I want the foreground RAM to stay where it is. But the way I've got this wired right now is I have all the address lines wired between the background RAM and the foreground RAM, which meaning they're both using the same set of addresses. So what I need to do is I need to uncouple these. I need to use these two transceivers, which are currently being used to handle the output of the adders for the background RAM, but they will also go to the foreground RAM. So I need to get rid of those and reuse these, use these for having a separate set of addresses for the background RAM and the foreground RAM. So I need to, instead of these wires running between them, I need to run these wires from this chip over to here, and I need to run the input addresses into these two transceivers. Then what I want to do is I want to take this whole thing and board and shift it up so I can add more transceivers here. I need 4 transceivers. I need background RAM transceivers and foreground RAM transceivers that are for the use of the video card. So those will be active during the display interval, and these others can be active. These will be active only when we're not in the display interval and when we're talking to when we're talking to the appropriate addresses. Then those transceivers will be active. So I need to move those up. Finally, I have these two coupled. I put this NOR chip in here because I had space for it, and I didn't have space on this board. But really, I want to put all the logic for the interrupt handling on one board. So I want to redo that. And then I'm going to use a board above that yet will handle all of the stuff related to registers. So these two registers need to move up into that board, and I'm going to have some more registers. I want to be able to, when I have a collision, I want to be able to, when I have a foreground background collision, I want to be able to read the location of the address counter of the video card, so I know where that happened. So I need registers for that too. So those are the changes I have to make, and it's going to be fairly big. It's quite a few things need to be rewired. So I'm going to have to uncouple things, move this board up, put those there, make some changes in here. When I get that all working, then I hope to be able to start actually writing some display codes that you can actually see what the output of this thing looks like. Thank you very much. And so I'll see you as soon as I possibly can.